So, we will now go through the last algorithm in the deadlock detection. So, we have seen a lot of deadlock detection, and this is the final model in which we will study the problem, and that is the most generic model, as I was mentioning in the end of the last lecture, that we are going to look at Pi out of Qi model. So, every process I requires P out of a given set of Q resources. So, it is going to send request to all Q of them, and as soon as it gets replies from P of them, then it can proceed. Okay. Now, here we are going to use a slightly different sets of messages also, that when a process wants to request for the resources, it will send request messages, and the reply messages are the messages that are necessary for unblocking the process. So, once it gets those replies, that means it has access to those resources and it can now proceed. So, it means that if it is a P out of Q request model, then if you get back P replies, then you are now able to proceed, right. So, we are going to have two, we will study two algorithms. The first algorithm is basically the way in which the resources are requested and granted, because this model is the actual computation, the computation which is taking place by the processes as they are accessing the resources. That is the protocol for accessing the resources, and that protocol can lead to deadlock obviously, and we will have the deadlock detection algorithm sitting on top of this to detect whether a deadlock is happening, alright, and that will take place by doing what we will do is we will do a global snapshot, and by taking the global snapshot we will try to see whether there is a deadlock. Okay. So, first we will look at the model. Okay, this is not the real algorithm, this is the model for accessing the resources, this is the protocol for accessing the resources, right. So, for this we have wait I is a boolean, and wait I becomes true when you are blocking, in the sense that you are not getting P out of the Q resources. So, therefore, you cannot proceed at this point of time. So, you set wait I equal to true, the process I sets wait I equal to true. Ti is the current time at process I. In I is the set of nodes whose requests are outstanding at I. So, this is the set of inward dependencies. The process I is holding on to some resources, and the in I is the set of processes which are waiting for those resources. Okay. Right. So, for process Pi, the node corresponding to process Pi, this in I is the set of incoming edges. Out I is the set of nodes on which I is waiting. So, this is the set of outgoing edges. Obviously, if you take the set of processes and the in I's and the out I's, then this actually defines the wait for graph. Okay. Pi is an integer which indicates the number of replies required for unblocking. Okay. So, if you get Pi replies, that means you have Pi resources and you can proceed. Wi is a real number which we will use later on as the wait for termination detection. It is the local wait of the process. Okay. At this point of time, we are not interested in Wi, but later on we will talk about Wi. Is this clear? What we need to remember from this is the status of the process in terms of wait I, whether it is blocked or not blocked. We need to remember that in I is the set of inward dependencies, out I is the set of outward dependencies, and Pi is the number of resources that we want. So, it is also the number of replies that we need for unblocking. Right. So, when a node blocks on a Pi out of Qi request, it sends a request send I. Okay, so what does it do? For every node j on which I is blocked, what we do is we set out I is the set of outward dependencies. So, we add j to that because it is blocked on j. This is where we are creating the set out I, and we send a request message to j. Okay, request I message to j, and set pi to the number of replies needed. Who decides the value of pi? The computation, the real computation that the process is doing. So, it knows how many of those resources are needed before it can proceed. So, that value is set to be pi, and we set wait I equal to true. Okay. All this is done if the process blocks on a pi out of qi request. All right. What does a node do when it gets a when it receives a request by node j? Okay, when it gets a request made by node j, it just includes j in the set of inward dependencies, right, because j has sent it a message. So, it is waiting for, so j is waiting for some resource held by I. So, it is one of the inward dependencies. Then we look at reply send j, okay, executed by node I when it replies to a request by j. When j sends a request, and finally when it is in a position to reply, then this is what it will do. What will it do? These are procedures, by the way. We are going to show the actual protocol where these procedures will be called. So, what is reply send j? We remove j from the set of inward dependencies and send a reply to j. Okay. This will be done when j when the node I is able to reduce itself. When it is able to reduce itself, it will then send replies back to its inward dependencies, right, saying that I am going to free this up. Okay. So, this reply message is actually a message which tells j that I is freeing up the resource for which j is waiting. Okay. Reply receive j, this is executed by node I when it receives a reply from j to its request. Okay. Executed by node I when it receives a reply. So, it first checks whether this is a valid reply for the current request. If it is a valid reply for the current request, now see, these algorithms will run many times during the lifetime of a computation. So, we have to distinguish between outdated requests and new requests, and outdated replies and new replies. So, if it is a valid reply for the current request, then we set out I to out I minus j. So, we remove j from its outward dependencies because it has already responded, and we set pi equal to pi minus 1 because now we need one less resource, because already the resource which j was holding is now in my ownership. So, I need pi minus 1 remaining resources. Now, if I find that after this pi becomes 0, that means I have got all my resources. If I have got all my resources, I set wait I to be false, and then for all k belonging to out I, we send cancel I to k. Now, which are these k belonging to out I? Who are these people? Right. So, it was waiting for pi out of qi. It has got pi replies. Now, to the remaining qi minus pi nodes, it sends a cancel. It says that I do not want it anymore because I have got my pi resources. So, I do not need it from you anymore, right. So, that is what the cancel I message is going to tell them, right, and then out I is set to empty, because now it has no outward dependency. When it has reduced itself, there is no more outward dependency. And what does a node do when it receives a cancel message? It simply removes the sender from the inward dependencies, because it knows that it does not depend on me anymore, right. Now, this defines the protocol by which resources are accessed. So, how are the resources accessed? When we first, a node wants to get pi out of qi requests, it sends the request messages to all the qi nodes, right. When a node is able to complete and return its resources, it sends a reply message to those nodes which are on its inward dependency. So, let us see what it, just let us recall what it does. When it sends a reply, okay, it will send the reply message back to j. The reply message is actually a message which gives the resource to the this thing. So, it is not dependent on that anymore, and when the reply message is received, the node which receives the reply message sees whether it has got all the replies, necessary replies, a pi number of replies. If so, then it is able to complete now. So, it sends cancel messages to its other outgoing edges, and otherwise it, after that it uses the resources and goes ahead, right. This is the way the whole thing works. The cancel is redundant. No, we did not, we skipped one part here, is when you are receiving, when you are done with the resources, will you reply back to all of your inward dependencies or not? That is something which we have not said so far, right. So, that will also is also related to this cancel. I mean, yeah, see, I am holding a resource, okay. You have made a request for that, he has made a request for that. Now, when I am done with it, am I going to send both of you replies, or am I going to send one of you a reply, or what am I going to do about that? Okay, that is an important thing, because if replying to both of you gives both of you the impression that you are getting that resource, then we have a problem, right. So, are we actually sending both replies to both of you, or what are we doing? So, that we have not yet mentioned here, right. So, that will also determine whether I need to know that you don't need the resource anymore. So, if you send me a cancel message, I will know that you do not need it anymore. So, in that case I might just send the reply to him. Are you getting my point? So, that part we are not yet there right now. Let us go ahead. Right. So, we are going to look at the algorithm which is going to do the deadlock detection. Okay. So, let us look at the data structures that are used here. Just give me a minute, I will just check out one thing. Okay. This is an algorithm which is going to work on top of this model for accessing resources, alright. Now, this data structure will be used by the deadlock detection algorithm. The data structure consists of an array 1 through n of records, which this array of records will be called LS, okay. And this these records will have the following fields. Okay. This array 1 through n of records will have the following fields. So, it will have an out field which has the nodes on which I is waiting in the snapshot. Okay. It will have an in field which has the nodes waiting on I in the snapshot. T is the time when init initiated the snapshot, so that we can compare two different snapshots initiated at the same node by virtue of their timestamps. Init.s, which is the local blocked state as seen by snapshot, and p, which is the value of pi as seen in the snapshot. So, this gives you an idea of what the global deadlock detection algorithm is trying to capture. It is trying to take a global snapshot of the system and find out who is waiting for what, right. So, at every node it wants to take the snapshot of that node. So, what is that snapshot it wants to take? It takes it wants to see what are its outward dependencies at that point of time, what are its inward dependencies at that point of time, what is the time at which this snapshot was initiated, what is the state of that process when the snapshot is taken, that is blocked or unblocked, and what is the value of p at that point of time. So, how many resources does it still need to make progress at that point of time. Okay. This is what the algorithm will try to capture, and once it captures that, it will use that snapshot to detect whether there is a deadlock situation, right. And how will it try to detect a deadlock, whether there is a deadlock situation? It will try to reduce this graph. How will it try to reduce the graph? It will see that is there any node in this system for which pi request can be granted. If it can be granted, then that node will get reduced, and then that might free up some resources, and then maybe some parent of that will be able to reduce, right. In this way, if you are able to reduce the whole graph. Now, I am not going into the details of this reduction algorithm, because that is not going to take place in a distributed way. Okay. So, let us see how this global snapshot detection algorithm takes place. The distributed WFG, wait for graph, is recorded using flood messages in the outward sweep. So, we will use a flood messages to propagate the snapshot collection, and is examined for deadlocks using echo messages in the inward sweep. So, what will happen is, let me explain how this is going to happen. The initiator of the deadlock detection algorithm will send out a wave of flood messages. Okay. When the flood messages receive individual nodes, they will try to see whether I can reduce, right. The node which does not have any outward dependencies will immediately reduce, right. When it reduces, it will send the echo messages back to its parent on the wave, right. Now, when suppose you do not have any dependencies, but I am waiting for a resource held by you. So, when the flood message reaches you, you see that I do not have any dependencies, so I will complete, right. So, you will send an echo message to me. When I get an echo message to you, I will know that he has promised that he will complete and give the resource to me. So, out of my pi, I have got 1 from him. Okay. Then I have similarly sent out flood messages to him, and then when he sends his reply, then I know that okay, that request is also guaranteed. Now, please remember that at this point of time, he is not actually releasing the resource. All that he is saying is that I know that I can complete, and then I will at some point of time return the resource to you, right. So, I know that it is assured that he will complete and give his resource to me. So, now I have confirmation from you that you will give your resource, I have confirmation from him that he is going to give his resource. So I now pool all that conformations and see whether I can get pi conformations. So these conformations are through echoes. So if I get pi echoes, then I know that I am assured of getting pi of those requests. So then I can also complete, right. So at that point of time I reduce myself and send my parent an echo message. Now is that clear? Right? Echo is the name of the messages, right. So there are the outward the wave flows outwards using the flood messages, and these echoes are the conformations that help in reducing the graph, right. Now when finally if the initiator is able to reduce itself, then it knows there is no deadlock. It knows that I am not in a deadlock. All the initiator is interested to know is, am I in a deadlock, and if it is able to reduce itself, then it knows that I am not in a deadlock, right. Now please again remember that when it reduces itself, it does not mean that it has completed using its resources. All it means is that it has conformations and conformations of conformations that finally it will be able to complete, right. That is what it means. Now if it is able to reduce itself, then it knows it is not deadlocked. But what if it is not able to reduce itself? How does it know that it is not able to reduce itself? How will that happen? That will happen if that you get pi out of qi deadlocks, right. So some node I am not being able to get pi out of qi, right, because there are cycles in such a way that I cannot get pi out of qi. In that case what will happen? We need termination detection algorithm to figure out that it will not reduce, right. And when the termination detection algorithm tells us that the algorithm is complete, at that time we will say that we are in a deadlock, right. So for that termination detection algorithm, we will use a message called short message. What is a short message? It is the control message which sends the weight back from a node to the controlling agent, right. So that is the short messages will be used by individual processes to send their weight back to the initiator, right. Now let us dive into the algorithm. So the distributed wait for graph is recorded using flood messages in the outward sweep and is examined for deadlocks using echo messages in the inward sweep, right. Blocked nodes propagate the flood, active nodes initiate reduction with echo messages. Okay. A node is reduced if it receives echoes along pi out of its qi outgoing edges, right. When an echo arriving at a node does not unblock the node, its weight is sent directly to the initiator using a short message, right. If initiator is not reduced but termination is detected, then we have a deadlock, right. Now let us go into the actual algorithm details. This is the initiation, the first step of the algorithm, executed by node I to detect whether it is deadlocked. Okay. So it sets init to be equal to I, because that is the initiator. It sets wi to 0. Oops, I think it should be wi equal to 0 is dicey. I will check this out. I think it should be 1, right. I think the weight should start with 1. Okay. I will check this out. Okay. Now what you do is set out I to be equal to out I. What is this out I? Where does it get this from? You remember the data structures used in the resource access protocol. At that time when you want to access a resource, you send out request messages, right. So, and then you create the out I set, that is the data structure out I at process pi, from which we copy this set into this out. Okay. What is the in at this point of time? It is 0. Okay. We set it to 0 at this point of time, because we want to take a global snapshot. At this point of time, there may be some inward dependencies recorded in ini, but I will not use them, okay, consciously. Then I set the initiation time to ti, which is the current timestamp at this node. Then we set the state s to be equal to true. Okay. Then we set p to be equal to pi, where pi is the number of processes on which this node is still waiting. Remember that pi changes with time, because in the, if you remember the request access model, whenever you get confirmation from somebody, you decrement pi. Whenever a request is a reply is given to you, you decrement pi. So, this is the current value of pi. Then what we do is we send flood messages. This node propagates the flood message to each j in its out I, to each of its outgoing dependencies. And what are the things that are there? The name of the initiator, the name of the sender, the time at which the message at which the snapshot is initiated, and this is the weight. Okay. So, it distributes its weight to among these out I processes and sends it. All right. Now, okay, so this is 0. Okay, no problem with this. See, what's happening here is the node is not saving any weight for itself. It is just setting wi to 0. This is going to add up later on, right? And it is distributing all its weight to its outgoing messages. So, this is correct. This is 0. Okay. Right. Now, let us see flood receive. What does a node do when it receives a flood message from j? So, there are several cases here. So, the first case is that when ls init dot t is less than t init. T init is the timestamp on this flood message. Okay. And what is ls init dot t? It is in the local data structure of the node I. Okay. This is the timestamp of the last wave that was received from this initiator. Now, please understand this. What does this ls init give? Ls init is the data structure kept at node I for waves initiated by init. Okay. So, for each initiator, this ls data structure has a record, right. So, for waves initiated by him, I have lsi. For waves initiated by him, I have lsj. Okay. Now, what is ls init dot t? It is the timestamp of the last wave that was received from with init as the initiator. Okay. Now, if that is less than t init, what does it tells us? It tells us that this is a new wave. This is a new wave from the initiator init. Init is the initiator. Okay. This is the new wave from the initiator. So, if it is a new wave from the initiator and j belongs to ini, what does this means? J belongs to in I, that it is in the set of inward dependencies. So, this is a valid flood message because J belongs to in I, and it is a new snapshot because this ls init dot t is less than t init, right. So, what do we do in this case? In this case, we set ls init dot out to be equal to out I. So, this is the capturing of the state, we captured the local state. What do? By we save out I into out, we set ls init dot in to be equal to j at this point of time, we set ls init dot t is to equal to t init, we update this figure, and we set ls init dot s to wait I. Which one?
ls init in j.
This one? No, we start it here. See, this is not in j, this is the snapshot that you are collecting now. So, you have got a flood message from j, right. So, you are just recording j as in your inward dependencies. Your in j can have other nodes, but we do not know whether those dependencies are still there or not, right. That is why we do not put them in j at this point of time. Okay, we are not putting them in this in. So please remember, it is very important to remember that ls init dot in is not the same as in I. Okay, we just start by putting this j in this, and we will update ls init dot in due course of time. Okay. So, this is collecting the local snapshot, and then it checks whether wait I is true. If wait I is true means that it is waiting, okay. Then it sets ls init dot p to equal to pi, which is the number of resources it still needs, and it sends flood messages to each k in out I. Along each of its current outward dependencies, it sends the flood message, right. And what is the flood message? See, the sender is I, because this is the node I that we are talking about. The initiator is the same, we just copy init from that to this. The time of initiation is also the same, we just copy this here and this here, okay. This wait w is divided by out I and sent to the outgoing nodes, right. Is that clear? What are we going to do if wait I is false, that is this node is not waiting anymore? Then we must initiate the reduction, because then you have reached a node I which is not blocked anymore. If it is not blocked anymore, then ls init dot p will become 0, because there is no more, the number of processes on which you are blocked is now 0, and you will send a echo to the sender, right. You are sending the echo to the sender. Now, look at this carefully, you are not sending to everybody which is in I, you are just sending it to the one from which you got this flood message, okay. You are sending this back to that node, right. And we set ls init dot in to be equal to ls init dot in minus j, because it is no longer in the set of inward dependencies, right. Is this part clear? Yes or no? Clear?
That also increment.
We will do that when we will get we will see in due course of time, when we get see, this flood receive can reach a node along multiple paths, right. So, we will see that there the in will get incremented. Okay. So, this is only one case that we have looked. This is the case where this is a valid flood for a new snapshot, but you will get valid flood messages for the current snapshot also, right. So, let us go to that next step. Yes.
So one time we are assigning J, we are not doing union, here we are reducing J. Not in this equation, we can do phi also, like ls init in is equal to phi.
ls init in
the last
here in this one?
No, last one.
This. Yeah, we are just removing J from the set of inward dependencies.
The only possibility that only J will be there.
No, see that is because you are looking at for this case.
Yes, for this.
It's
Because we could have received the flood from two different from the same initiator. We can receive the flood from two different nodes. In that case,
we will see that case where we will get a valid flood message for the current snapshot. Okay. But I think for your case you are right, but because this is the first, this is a new snapshot that you are getting, and when it is a new snapshot, obviously you are getting it along J only. So, at that time only this is in the this thing, right. So, in this case most likely it will be same as writing this as empty. Okay. Right. Now, let us look at the other cases. Yes.
new snapshot. So at this point, the current rate will be 0.
See, here we are not storing any weight on the nodes. We are just whatever weight that you are getting along this, this weight is getting distributed straight away along your outgoing edges, outgoing these things. And if it is, and if you are not blocked, then what you are doing is you are sending that weight back along the echo. See, this weight W as a whole is going back along the echo, right. Now, let us look at this. If we see that ls init dot t is less than t init and j does not belong to ini.
Sir, one point, if you are not storing the weight, then you might be just sending what's the point? What are the dividing the weight? You can just send a signal.
No. Weights are important because you need to figure out whether the algorithm will terminate or not, right. So, every message should have weight.
But the node is not storing a weight. So how do you the termination protection efficient?
So, node is not storing a weight because every node, when it gets a flood message, it will either propagate the flood or send the weight back along the echo, right. But each of these, the echo or the propagation of the flood, must carry the weight forward. Otherwise, you see there will be some, if you send a message without weight, you will not know whether the node that receives that message is what it decides, whether it is going to complete or not complete. That information will never be available back with you. Now, if it cannot complete, it will send echo. If it can complete, then it will.
If it can complete, it will send echo back.
And there is a third category which we have not, we will come to that shortly, just give me some more time, when it will send the weight back to the controlling agent, to the initiator. Okay, let us go through these cases, it will become clear. Second case is that when this is less than t init and j does not belong to ini. Okay. Now, see what is the problem here. The problem here is that this is a new snapshot, okay, because in the data structure at I, the wave that was initiated by init had a timestamp t, and that seems to be less than the flood that is received along this. So, this is definitely a new wave, right. But we find that J does not belong to init. What does that mean? This means that the new request has not come here. If the request has not come, but the flood has come, right? How is that possible? Request has not come, but the flood has come. Is that an error in the algorithm? Error in the message? So, okay, is it possible by the following way, that there was a dependency, right? So, this node J was there in init, but now the node I at some point of time release that resource, right? So, if it release that resource, then it will send a reply back to that node, right? Now, that reply message is in transit, but when you send a reply, you are going to take it off your init because it is no longer in your inward dependency set. So, it is not in your init, the reply is in transit, and at that point of time the flood comes in, because the node J has not yet received the reply. So, it still treats that as an outward dependency, right. So, in this sequence this can happen. So, what should node I do when it gets this invalid flood for a new snapshot? It will simply reduce, it will send the echo back. That is what exactly it does. It sends echo with all these parameters init, t init, w back to J, right. Now, let us look at this case, that ls init.
But then sir, I gets 2 echoes or
No, you are confusing with the echo and the reply. There is a protocol for accessing the resources that uses request, reply, right, and cancel. This is flood and echo. This is the termination, this is the deadlock detection algorithm which is sitting on top of that. Are you getting me? Now, look at this case, ls init dot t is equal to t init, which means that it is the current wave, and J does not belong to init. So, again this is an invalid flood, but for the current snapshot, and the action will be exactly similar, right. We just send an echo, okay. The last one is that this is equal to t init, which means it is a current wave, and J belongs to init. So, this is a second flood that it is getting, it is not the first flood, because when it got the first flood, it updated this to be equal to this, right. That is when it updated it. So, now this is a current snapshot, I am getting a second flood, okay. Now, it checks its state. If its state is false, that is it is not blocked anymore, it sends a echo, right. And if it is still blocked, then what is it going to do? It will add J to its set of inward dependencies. See, this is where the in is getting updated. So, it is going to add J to its inward dependencies, and it will send a short message to init. This short message is carrying the weight that came along this flood, that is this W. This weight is being sent to init directly, the controlling agent, right. Okay.
flood message will come in a loop. The second flood message will come when
Second,
flood message. It will receive the second.
it can come in two ways. It can come from a loop, or it can come through two converging paths. In both cases, if it is still blocked, it will simply send it back. Now we have to digest why that is correct. Now you see that if let us first take the extreme case. Suppose we are looking at a single loop. Okay, so let me first take a single loop to explain one extreme. Okay, and let us say that this is all 1 out of 1 model. Okay, 1 out of 1 model. Now let us see how the flood messages will go. This one will send a flood, this one is blocked. So what will it do? It will send the flood. Okay, so what is the weight on this flood? 1. What is the weight on this flood? 1. It will propagate this flood with a weight of 1. It will propagate this flood with a weight of 1, right? And what does this do? It will use a short message to send this weight back to the initiator. The initiator gets all its weight back, so it understands that this is a deadlock, right? Okay, let us look at another case. This is P1, P2, and let us say that we are working with this one needs just 1 out of 2. Okay, suppose P3 needs 1 out of 2, and for all of them other ones it is 1 out of 1, right? So let us see what happens. Flood with a weight of 1, then again flood with a weight of 1, flood with 0.5, flood with 0.5, right? Then flood with 0.5. When it reaches here for the second time, it will short this to 0.5. Now P1 has 0.5 back. What is this one going to do? It will echo, right? So when it echoes this, then I wish I had another color. Anyway, this is echo of 0.5. When it what will P3 do when it gets this? It will reduce, right? So it will send a echo of 0.5, right? What is this going to do? Again echo. Now P1 will reduce, so no deadlock, and also the algorithm has terminated because 0.5 plus 0.5 is 1, right? So let us understand this thing, that echo messages, so this wave algorithm is going to create a tree, right? Echo messages are going to come back along that tree, and they will reduce each of the nodes as it comes, right. Whenever something cannot reduce, it is still blocked, it will send the wait through a short message to the initiator, right. That is how this is going to work, right. Now, unfortunately, I have also, we have to go into the details of this, what we do when we get an echo, what we do when we get a short, etc., but we are desperately running out of time. Okay. So, okay, just let us quickly go through this. What do we do when we get an echo? If this is something which is greater than t init, then this is very strange, because that means that this is an outdated receive message, right. So, that has to be discarded, right. This is an outdated one. So, if an outdated echo is received, we just discard the echo. This can never happen, that ls init dot t is less than t init, you are getting an echo, but you never got the flood, that cannot happen. So, this is impossible. If you find that they are both equal, then this is an echo for the current snapshot. So, what do? You take this out from your set of this one. Note that out I is not changed, it is only ls init dot out which is being changed. Okay. So, the data structure of the deadlock detection algorithm is changed. So, we remove that from there, then we see if it is still blocked or not. If it is not blocked, if it is blocked, then we send this through a short message to init. Okay. Otherwise, what we do is we reduce this p, because now you have one less this thing to get, okay. And if you find that this becomes 0 after that reduction, that means that this node can now reduce. If it can reduce, it will set this to false, and if init is equal to I, then it will declare that not deadlocked, because the initiator has reduced itself, then there is no deadlock. Otherwise, if it is not the initiator, it will send a echo message, okay, to all the nodes in its current inward dependency. Now, see, here also the weight is split among the set of inward dependencies, and this echo is sent to all the nodes in its inward dependency, right. And if you see that this p is not equal to 0, that means that it is still has to wait for some more nodes to release their resources, it has not got all the echoes, then for this echo, whatever weight it got, it will send it to init through the short message. Okay. So, only the last of these will go through the echo, the last weight will go through the echo, all the previous weights whatever it gets will be sent to the initiator through short. What does a node do when it gets a short message? If t init is less than t block I, then it discards the message, because this is an outdated short. If it is greater, that is not possible, you cannot get a short message for a flood which has not yet been initiated. If we find that it is for the same wave, but S is not blocked anymore, then we discard, and if it is blocked, then we add this weight to Wi, and if Wi becomes 1, then we declare deadlock and abort. So, this is the only place where we declare the deadlock, that is, we find that the sum of the weights has become 1 and still the node I has not been able to reduce itself. So, that is a case of deadlock, right. I want you to go over this algorithm once again, right, and please get back in touch with me if you have any doubts about this.